Welcome to this session. My name is Renee McCormick, and I'm with the National Math and Science Initiative. This session is going to deal with balancing redox net ionic equations. Now, having said that, I have some disclaimers to state as well. First of all, I did not write these lecture materials. I want to give credit to my good buddy down in College Station, Bryan College Station, Texas, which is she's named Kristen Henry Jones. Miss Jones has been teaching AP Chemistry remarkably successfully for a very long time at that school. And she's a sweet little blonde who is just an incredible AP Chemistry teacher. And she did a fine job with these notes. Have never felt the need to rewrite them because I couldn't do as well. So with her permission, she has allowed me to use them for many, many years. She did revise them in 2010. And so I've got the latest version, but there may be older versions circulating out there, and the rules of this game have changed. If you've listened to any of the other recordings on net ionic equations, this particular section with redox is absolutely ridiculously long. There's like 40 some odd of these to do, and I'm gonna do them all, but there is no reason for you to listen to all of them once you start to get it. You can work them, you can double check your answers, and move on with your life. There is much to memorize. There is much to master. Okay, that's the bad news. The good news is, with the format change that happened to the test back in 2007, we don't ask a tremendous number of these really difficult redox. I'm going to show you the redox so you'll have them as a resource and so that you can learn to do this, because you will have to master this, because there are multiple choice questions that have you do some redox balancing. And it's really kind of fun. If you like puzzles, if you're one of those kids that likes puzzles, I kind of like puzzles. To me, I just look at it it's kind of a puzzle, and I'm just trying to solve the puzzle. Now, there is some memory work to be done, as with this entire concept of net ionic reactions, and there is balancing to be done. You're not going to see the uber difficult ones, and I'll point them out as we go along, on the real AP exam now, because back in the day, we did them net ionically without having to balance them, and so we weren't worried about doing the two half reactions and getting a balanced equation. We were more interested in who the players were. Who are the players that are the reactants? Who are the players that are the products? However, now with the balancing, these just got a lot more tedious and would take a lot more time. So I promise you, I'm telling you the truth as I know it today. Since 2007, any of the redox equations that have shown up on the AP exam are far easier than some of the ones that you're going to encounter. And I will try my best to sort for you which ones would be likely candidates to show up these days and which ones you most likely would never see these days, just for the simple sake of time, your time on the AP exam. If you've not heard me say this before as well, there are some strategies that we use to speed this little process along. You may have been taught to write a molecular equation and then cross off the spectators and then go straight into a net ionic. You won't be seeing me do that at this stage of the game. I did that back on the double replacement sorts of reactions back in the early days of these recordings. And so by the time you get to redox, you're fairly well through all the different types of the equations. I'm so sorry. I apologize. I'm a little under the weather today. So if I don't sound like my usual perky, adorable self, please forgive. And if I cough in your ear, again, I apologize in advance. I'll also stop from time to time and take a drink because my throat's giving me some trouble today. But I will trudge on and quit whining about it. So, oxidation reduction reactions. This is the beginning of these recordings. There will be many, probably 4, I'm guessing, because, like I say, these are going to take a while. So, let's kind of get the ground rules played out here. With oxidation reduction, meaning redox, first of all, you must know what redox means. It's a shorthand way of saying reduction and oxidation half reactions. So there will be some half reactions to be written. When you get stuck trying to balance these by inspection, then we go to the half reaction method. You'll see me do that a lot. Reduction, I use the mnemonic device, oil rig, being from Texas, where oxidation is loss, reduction is gain of electrons. Write the half reactions, and then make the equations balance. And I'll give you the rules as we go along. It's one of those things that it's almost easier to just see and do than it is for me to like lay out the rules and then you memorize the rules and then we do it. It's if you'll just dive in and do it with me and have a little bit of faith, I am asking for a slight leap of faith, then I think this will make way more sense to your brain. So oxidation numbers are something that you know how to do, and the oxidation numbers of at least 2 of the elements have got to change. Ooh, at least 2. All right, so we're going to run into 3 different major types of redox reactions. The normal, typical type that is in most textbooks, and most textbooks dwell on it ad nauseum, is where one thing is oxidized and yet another thing is reduced. But it is possible to have the same thing being both oxidized and reduced, and it can go in 2 directions. If one thing is a reactant and it is both oxidized and reduced to form 2 different products, then you have a disproportionation reaction. But we can also reverse that puppy. We can have the same element, and the halogens are kind of famous for this. We can have the same element show up maybe as chlorine gas or chloride ion, as well as in a polyatomic ion involving chlorine, of which there are many different oxidation states for chlorine, and they can both converge on say Cl2, which has 0 oxidation state. So we'll review a little bit about oxidation reduction rules, but you'll have a better discussion of that if you listen to the electrochem recording that actually addresses it as a first teach from scratch, I know nothing kind of moment. All right, so single replacements and some combination reactions and some decomp reactions are also redox reactions. So there are no finite lines that divide the different types of reactions. Those lines get a little blurred when you get more advanced into chemistry. To predict products of a redox reaction, we have to look at the reagents that are given to see if there's both an oxidizing agent and a reducing agent. I remind you the oxidizing agent is itself reduced, and the reducing agent is itself oxidized. So when a problem or when one of these prompts mentions an acidic or basic solution, it's probably redox. So that should get your antenna up. If it says it's acidified, or if an acid or base is present in the reaction, then you've basically got 2 options. It's either a neutralization or redox is the culprit. Then there is some flat-out memory work to do. I make no apologies for that. In my profession, people frown upon having students memorize things. Yeah, if that was the case, none of us would be able to spell because we wouldn't know our alphabet. So I make no apologies for saying from time to time, there's just some things you got to give up and memorize. So if we are dealing with manganese, which makes ridiculously high oxidation states, it would be a +7 in permanganate, and it would be a +4 in MnO2. If we are in acidic solution, then you're going to reduce it down to Mn2+. If you have permanganate in a neutral or basic solution, then it's going to form the solid MnO2. You have to just kind of memorize that. And then this one's easy. Dichromate is going to always go to Cr3+. Did you see Aaron Brockovich? There are 2 basic forms of chromium. One is carcinogenic and one is not. The Cr3+ is not. The one that Aaron Brockovich dealt with the tainted public water supply was hexavalent chromium, as they kept saying in the movie, which means the oxidation state on that chromium is +6. Do the algebra and figure out why. 7 minus 2 is for the oxygens is -14, but 2 of them are going to be in the charge, so I'm really looking at -12, split over 2 pieces. That would be +6 piece. Concentrated nitric is going to make NO2, brown noxious gas. I beg you to look at apchemistry.nimsy.wikispaces.com and watch the Ira Rimson demo, because that's the brown gas that is formed when we react metals with nitric acid. It is known as the oxidizing acid and is a strong acid. If we have dilute nitric acid, then we don't have as much capacity to make NO2, and we make NO instead. If you take hot concentrated sulfuric, then you make SO2. If you have a metallic ion, it will go to an us ion. If you have a halogen, it will go to a halide ion. Don't let those words scare you. That's just super easy. So if I have Fe3+ and it's going to be reduced, it can go to Fe2+, or it could also go all the way down to FeO. And a halogen, that's not an H2, so sorry, something like Cl2 is going to make 2 Cl minuses. Then we get into peroxides. We have this peroxide and this peroxide. So this peroxide, the sodium peroxide, is going to make NaOH, which in solution is going to dissociate because it's a strong base. And hydrogen peroxide is going to make water and oxygen. And that's why we keep it in a brown bottle, because your little bottles would explode as the oxygen gas accumulated in there, and it would make quite the mess when you've decomposed your hydrogen peroxide, and to find out it's just a water solution that's busted the container and spilled all over the place. And then if we have the strongest acid of all in a reaction, HClO4, one of the products that's going to happen is Cl-. So think about HClO4 and what the oxidation state is of the Cl there. It's going to go to Cl2 with a 0. Obviously you'd have to double this, but within this molecule, that's -8 right there. That's +1. We have rules for that say that's always the case. Oxygen's always -2 in a compound unless you're in a peroxide, and then H is always +1 unless you're in a hydride. So that means this has to be +7, this one entity right here, to make that entire thing add up to 0 in a neutral compound. So +7 down to 0 is a whole bunch of electrons being transferred, huh? More rules. Matter of fact, what I would do if I were you while you're practicing these is I would print this one page and keep it handy and reference it over and over and over again until you finally use this enough that you memorize it as self-defense. Now, this is just going backwards. Halide ions go to halogens. Free metals will go to their ions. Sulfite ions, or SO2, will make sulfate ions. Nitrite ions will make nitrate ions. Get the it business? Ite, I should have said. Ites go to eights. Free halogens are going to make hypohalite ions in basic solution. In concentrated basic solution, they'll make halate ions, meaning 8 ending versus ite ending is all that means. I know it sounds all scary, but it just means we're going to make the ite ion or we're going to make the 8 ions. And we have several choices with the halogens, because remember they go like this: ClO, Cl, O2, ClO3, ClO4, all of which bear a -1 charge. So this one is hypochlorous. This one is chlorous. This one is chlorate. I'm sorry, did I miss something? No, that one is no, this is chlorite. I'm sorry, I'm thinking acid. Hypochlorite. I went all the way to the acid, sorry. And this is chlorate, and this is hyperchlorate. I focus on memorizing the ites, and the 8s ate one more oxygen, so I went from memorizing the fact it's ClO2- to it ate another oxygen, so it goes up to ClO3, and if it's really hyper, it's going to eat yet another oxygen, which makes ClO4. But this one is below by 1, so it's hypo, which is, you know, like under, prefix meaning under, like hypodermic needle, put it under the dermis, as opposed to hyperactive, way too much activity going on. They have medication for that, you know. So hyperchlorate, which most people get rid of the hyper and contract it to perchlorate, but don't put the apostrophe on it, which is a bit annoying. So you may know it more as perchlorate. All right, then peroxide, hydrogen peroxide is going to form oxygen and water. And oxalate, which is my personal favorite polyatomic ion. Everyone needs their favorite polyatomic ion. This one's mine. Get your own. Is going to make carbon dioxide. So we have a couple of examples. A solution of tin-2 chloride is added to an acidified. Big hammer hitting you over the head going redox, redox. Also, it's do this automatically. If you're going to acidify the solution, water is going to be a product. So you already know one of the products. And it's a solution of potassium permanganate. So potassium chloride is going to make a soluble salt, so get those spectators out of there. And you were just working with the tin-2 ion, acidify it, the permanganate ion. In an acidic solution, permanganate ion is going to make Mn2+. Tin-2, and you have to, again, you have to know some formula writing sorts of oxidation states and some of these more famous, more popular elements like tin. So tin comes in two varieties, tin-2+, tin-4+, and then if it's the metal tin, it's SN0 with the oxidation state of 0. So if permanganate is going to go down from a +7 to a +2, then somebody else has to go up, and the tin is the candidate that's going to go up, so it's going to have to go up to the +4. You can't have two things reduced, in other words. So if somebody's reduced, somebody else has to be oxidized. So a solution of potassium iodide is added to an acidified. Again, immediately write H+, and immediately write H2O, because we know that to be true. of potassium dichromate. So I'd make potassium, get the potassiums out of there. So I have I minus plus my H plus dichromate, which always goes to Aaron Brockovich, the safe, trivalent, 3 plus, chromium ion, and the I minus is going to go to your good buddy iodine. So we do have to balance these now. These are not balanced because these were older directions. Hydrogen peroxide is added to a solution of iron 2 sulfate. Sulfate's going to be a spectator, and we're going to have simply the redox reaction going on between H2O2 and Fe2 plus. That Roman numeral was your friend telling you it was the 2 plus. So it's got to go up because peroxide is this ion, and when we go to water, this is a -2 all by itself. So these are -1 each. So that's going up. It's being oxidized. So I minus is going to have to go down mathematically and be reduced to 0. Then a piece of iron, that's the metal. It's a word implying solid. So the metal iron is added to a solution of iron 3 sulfate. Again, this is a spectator. So we're just going to have Fe plus Fe3, and both of them land at Fe2 plus, because one of them had to be oxidized, one had to be reduced. So which was which? Well, that one's reduced, so this one's oxidized. This is a malproportionation reaction. Not a term you often see in a first-year chemistry college text. They usually save that word for later when you take an advanced inorganic course. Which I have to say, that and quantitative analysis were my favorite 2 chemistry courses for majors. But enough of my preferences. Onward we march. Let's look at some examples. Disclaimer. This is the toughest section of the net ionics. I'm not going to lie. I cannot lie to you. It is the toughest because you have to memorize some things. If you do enough of these, the memory work gets a whole lot easier. And this is about practice. You've heard me preach this, and I'm going to preach it one more time, so I hope I'm preaching to the choir. My technique for getting my students to be incredibly successful with this was I taught this early in the year. We did 10-minute doses every class period until we mastered all the different sorts. So the basic routine was I taught a new thing 10 minutes. They practiced when they had homework. They went home. They practiced 10 or 12. They came back in the next class period. I was on alternating blocks, so I saw them every other day. They came in. The solutions were worked out on the overhead projector back in the day. Now they'd be worked out in my swift little tablet PC and projected up onto a white screen. They would be all colorful, even with the overhead projector, because I believe color helps you sort your thought process. And they would check, and there'd be moaning and groaning and celebrations, and then I'd say, okay, put that away. Now it's time for a quiz. And then I would give them a new set of reactions to do. They would trade and grade, and then they would explain to each other, the person whose paper they graded, they would explain to each other what you did right and what you did wrong, and why you missed something. And of course there would be arguments, and of course there are more than one possible correct answers to most of these. I'm going to stick with the most logical correct answer, the most popular correct answer, but I don't have the time, the energy, or even the prowess to gaze into your brain and see if you went a different route. So I'm just telling you now that there could be more than the correct answers that you see me write on this recording. If you have questions, you should flag them. You should keep a running list, and that's why you have a chemistry teacher. You should go to that chemistry teacher and say, hey, is this a possible reduction or oxidation? Because I can go, a couple of different routes with this. And in the case of halogens, you can go 5 or 6 different routes with this. I'm going to stick with what is most, quote unquote, normal, what you would see most often as the answer in a textbook. But you do need to know there's many more than one correct answer to most of these little examples. After we did that and got through all the different sorts, then I would start mixing them up. And for the rest of the school year, first class period that I saw them every single week, everybody knew that they had a net ionic. So in the fall, most of my students were smart enough to figure out that they studied better as a pack, with a pack mentality against a common enemy, which would be me, with the ultimate red pen. And they would form study groups, and they would help each other. And I love it when you come up with clever, albeit corny or kind of silly or stupid ways to remember things, because that's when you know that you're really mastering a topic. So do that. Get into study groups if you're still suffering with this. Also, there's a recording on attack strategies, and if you're just desperate, you should listen to that, because that can speed you along a little bit too. I'm not proud of some of those attack strategies, but at some point desperation sets in. Alright, this first one is somewhat kind and gentle. We have iron 3 ions, so we know that one of our players is Fe3+, and it is reduced, so that was kind of them to tell me. So if these are reduced, then these are oxidized. So I- ions, iodide, ide being an ion ending for elements. So the halogens being halide ions, so I-. And so if Fe3+ is reduced, you could take it to Fe2+, or you could take it all the way to the metal. Again, more than one correct answer. Plus iodine, which has a 0 oxidation state. No, you don't have to put the 0. I do that to remind you that that's what that is. Any element in its standard state has an oxidation state of 0. Alright, so now we need to balance this, and we need to balance it not only by element, or by atom, I often say. So I need 2 I's on each side. But I also have to balance by charge. Total charge on the left is 3+ plus 1-, which is +2. Total charge on the right is I'm sorry, I didn't double my I. So let me try that again. It's 3+ plus 2-, which is only a +1, where over here I have a +2. So if I double this and double, that forces me to double this. Let's see how that works. This is a little bit of trial and error, folks. So this is +6, because 2 plus 3 is +6, 2 minuses is +4. So that reduces my 6+ down to +4 is what I probably should say. And then 2 times 2+ is 4+. So let me try that again. 2 times +3 is +6. 2 times -1 is a -2. Add those together, and I come out with +4. This is 0, and it's added to 2 times 2+, which is +4. Check. It balances. I've balanced by atom, and I've balanced by charge. We used to not have to do that. We used to have just written what you see in the screen is in blue and be done with it. And that's why doing the redox wasn't as tedious as it is now, but we have to balance now. So it may force you sometimes, when you get stuck and you can't eyeball it like we just did this one, you may have to go to half reactions, which is what's going to happen to me on the next one, because you know I've already worked these, right? Alright, so permanganate, potassium permanganate solution. Permanganate is always a candidate for a reduction because it sits there as MnO4-, which means it's the manganese in it has a +7 oxidation state. That's totally crazy. That's normally oxidation states are ±1 or 2 or 3 at most, but 4, 5, and 6 gets a little nuts. That's a lot of electrons to transfer. So it's always a candidate. It's purple in solution, so I'm using my purple pen. And it's added to concentrated hydrochloric acid. So we're going to acidify it. Remember that hydrochloric is strong, so you should be thinking it's going to be dissociated like that, which means the chloride ion, the halide, you need to get the hang of this, the halide may very well end up being a halogen. So I have potassium, because if I made potassium chloride, it's just going to be a spectator. So that 1A metal is going to be my spectator. So I put my permanganate ion in a beautiful purple. I add the H+ and the Cl-. And what will permanganate reduce to? It reduces to the more logical Mn2+. Because I have H+ on the left, I'm going to have water on the right, always, always. And I'm going to make Cl2 so that I can oxidize something. So I'm reducing the Mn from +7 down to +2. I'm going to oxidize the Cl- up to Cl2. And I can tell you right now that I cannot do this by inspection. It's a hairy equation. Anytime permanganate is involved, you might as well just give up and go to the half reactions. So let's do them. Here's the reduction. Here's the oxidation. I'm going to need more room. Who's reduced? MnO4. So start with MnO4-, and this is a common one, so embrace it because you're going to do it a lot. And it's going to go to Mn2+, and then the rules are I can add as much oxygen as necessary using water as the vehicle to balance the O's. I need 4. Well, now you've gone and done it. You've introduced H on the right with none on the left, so you can use H+ to get yourself out of this mess. which should make sense to you since H plus is sitting as a reactant in our skeleton equation above anyway. All right, so I'm going to now balance by charge. So plus 8 with a minus and a Mn2 plus. What have I got going on? I have plus 7 on the left total, plus 2 total on the right, and reduction is gain, rig. It's the rig part of oxidation, so I'm going to gain some electrons. I'm going to stay with purple. How many am I going to gain? I'm going to gain, I just did that math, it's going to be 5. One more time, where's the 5 come from? What's the total charge on the left before I add those electrons? It is plus 7. What's the total charge on the right? It is plus 2. What's the difference between 2 and 7? 5. So I add 5 negative charges to the plus 7 side to make it reduce down to plus 2 total. All right, so the oxidation, this is an easy one. Cl minus goes to Cl2. Obviously, I need 2 of those. What's the total charge on the left? Minus 2. What's the total charge then need to be on the right? Minus 2. So oxidation is loss of electrons. They come off as a product, and I need 2 of them. Well, now I've got my 2 prime numbers worth of electrons, a 5 and a 2, so I must multiply the 2 by 5 and the 5 by 2. It's a 2-5 trick. So come along and multiply everything up here by 2. Ta-da! Multiply everything down here by 5. Ta-da! 10 electrons on both sides. That was the goal of this game. Add this puppy together. Can you reduce anything else off of here? Always look for waters. Crap. Don't have any on the bottom. Always look for H pluses. Crap. Don't have any. So we are stuck with this big hairy mess of final reaction. This is why we don't do many of these anymore. In question 4. This could be a great multiple choice question though. Plus 16 H plus 10 Cl minus yields 2 Mn2 plus. I'm nervous right now because everything's an even number. Until I put in the 5Cl2 and the 8H2O. As long as I have a prime number in there, I don't have to reduce this whole thing down. All right, so to make sure I wrote everything right, correct, and I'm done. So that would be my answer. Wow, that's a lot of work, which is why you probably won't see one like this on the question number 4 in the free response, unless the other 2 are mighty easy. And you should do them first. Come back to this one. Keep an eye on the clock. Do not let question 4 eat up more than 15 minutes of your total free response time. I'd really like for you to keep it to 10, but I'll spot you a little bit because you're nervous. Alright, so what's the total charge on the left just to double check? 2 minuses, 16 pluses, and 10 minuses. Was that total out to be minus 14 plus 2? No. Plus 4. Yes, plus 4. And then on this side, what's the total? Nothing for this, nothing for this. So 2 times plus 2 is plus 4. Hallelujah. It balances by charge. I'm convinced I've done this correctly. All right. You haven't seen the elastomer permanganate. It shows up a lot. Now what? Magnesium metal. Okay, celebrate the fact it's a metal and write Mg. Is added to dilute nitric acid. All right, nitric is strong, so do this, which means I'm going to do this, and then do this, which means I'm going to do this. I'm going to make NO2. Oh, no, I'm not, because they go on to tell me, so forget that idea. Normally that's what we do. Magnesium metal added to dilute nitric acid, giving as one of the products a compound in which the oxidation number for nitrogen is -3. Well, that's a horse of a different color. So the only thing I know where nitrogen is going to be a -3 that has H's and H pluses involved is NH4 plus. So in order for this to carry a total of a +1 charge, knowing that each of those 4 hydrogens is +1 as if nitrogen is a -3. So that's a little bit of a curveball. And then I'm going to make the ion of the metal. So metals are going to make their most common ion. And I've still got the water. All right. Can I inspect this one? If I put 4 magnesiums on each side. Or not 4 magnesiums. Yeah, I'd have to. I'm going to have to go to half reactions on this one. So I'm going to need more room. What am I going to have? I'm going to have a reduction. I'm going to have an oxidation. Who's reduced? Well, clearly over here, this is a +5 nitrogen, so that's a big reduction, down to a -3, which they told us. So I would start with the NO3 minus going to NH4 plus, and we've got to get 3 waters over here to get those oxygens balanced, and that's going to force 6 H pluses right there. And now total charge on the left is +5, total charge on the right is only +1. So how's that going to work? Something is wrong. What have I done wrong? Oh, I'm a doofus. I didn't do the counting of the H pluses right. 6 and 4 is 10. That's going to change my charge, huh? Okay, one more time. That's going to be a +9 on the left, +1 on the right. So I need +8 electrons. I don't feel bad. I can do arithmetic better, I promise. All right, so 8 electrons. Now, I'm just going to double that charge again. 8, 9, +1 on each side. That's good. That's balanced. Okay, so what's going on with the oxidation half? That's the easy part. Mg, the metal, goes to Mg, the 2+ ion, +2 electrons. Whew. Okay, that's my reward for surviving the first one. All right, so now, what's the scoop? Well, everything on the bottom has to be multiplied by 4, so I can get to 8 electrons. That's how that happens, right? 4 of those, 4 of those. 4 times 2 is 8. Now that's the whole goal of this game, is to cross those off and now mush the rest together. So we get 4 Mg plus a nitrate plus 10 H plus yields 4 Mg2 plus ions plus an NH4 plus ion plus 3 H2Os. That's not an easy one to get started with. If you missed it, please do not feel bad about it. You just need to practice some more, because that one was tough. You saw me goof up and not read the whole thing and then try to make what's normal out of nitric acid, which is NO2 gas, but that's going to give nitrogen a +4 oxidation state, which is way, way different from a -3 oxidation state. So that one was just kind of mean. All right, this one will be easier. A solution of potassium iodide is electrolyzed. So if you've done electrochem, you know that we often run an electric current through a substance to split it out into its elements. Now, if we did that with potassium, we'd be sorry, right? So potassium would go kaboom, because it's a 1A metal, and that would be a bad thing. Lucky for us, that doesn't happen. Any 1A metal is never oxidized. Never. I don't get to say never very often. Never oxidized. Okay, or reduced. Would it be oxidized? All right, let's look at the next one. The solution of potassium iodide is electrolyzed. What does electrolyzed mean? That means we're running an electric current through it to separate it. So what are we going to make? Well, iodide is going to make I2. Easy enough. If potassium, which would be the K+ ion, goes to potassium metal, we have an explosion on our hands. That is not a good plan. And the truth is, if you think back to the electrolytic portion of the electrochem unit, 1A metals and polyatomic ions are never participating in these electrolysis reactions. So water takes their place instead. So my potassium is not going to be involved, but water is. So now you've got to have one more thought. If I- is going up to I2 0, this one is oxidized, so I need to figure out which part of water is going to take on the role of reduction. Well, this is a +1, that's a -2. We're either going to make hydrogen gas or we're going to make oxygen gas. If we make hydrogen gas, is that a reduction? Yes, from +1 down to 0 for H2. But if we tried that with oxygen gas, we would go up from an oxidation state of -2, we would increase to 0, and that would be another oxidation, and that can't happen. So it's got to be the reduction. So we've got to make H2 gas. These are called alkali metals because we make H2 gas and we also make OH-. So that's information that was back in the electrochem unit that you get to use on this question as well. So I'm going to do the easy part first. I'm going to take my I- and I'm going to make my I2. So we know that's happening. So again, I say I would need 2 of these. I'll do that in red so all my coefficients are the same. I'll need 2 of those. So now I've got a -1 ion, a pair of them, making a neutral compound. So that's an increase in oxidation state, so that's an oxidation. Now I need the reduction. So my other player is water. So the question then remains, what do I do? Well, if you've already just gotten as far as to establish it's a reduction, go to the reduction potential table. Find the reduction half reaction, take it, and write it down. Otherwise, reason with it. And like I just did earlier, I'm going to have to, it's got to be the H plus 1 in here that's going to go to H2 gas, which is what causes the kaboom in the first place if we did have the chunk of potassium metal doing this. So that's going to be released, and then it's an alkali metal, so I'm going to make OH. That's where it gets its name, because that's what it does in solution. So now that I've done that, let's see if we can do this by inspection. What's the total? Well, let's do, okay, H's first. I have 1 O, 1 O, 2 H's, 3 H's. Phooey. If I double this, I have 2 O's. It forces a doubling here, but it gets me 4 H's in the process. Yippee skippy. So now what's the total charge on the left? 2 times -1 is -2. What's the total charge on the right? 2 times -1 is -2, because these are zeros. And check, check, we're balanced and we're done. So that one was not so painful. All right, let's look at the next one. It gets a little more painful. Potassium dichromate solution, again with the potassium, is added to acidified, that's your clue that we're in the land of redox, if you didn't already know that, of sodium sulfite. All right, so these alkali metal ions are just spectators, so get them out of there. So let's think about what's going on. First of all, it says acidified, so make this easy. H plus and H2O. We know that much is going to happen. Let's deal with the dichromate. Cr2O72-. I cannot memorize your polyatomic ions for you. And that's always going to go to Cr3+. Then I take the sulfite and think about what's going on with it, because that's the only thing I've got left to play with here. So my sulfite is SO3 2-, where if 3 -2's are present, that's a total of -6, but the overall charge is -2, so that one lone sulfur has to be a +4. And I've already got a reduction going on with my +6 chromium being a +3, so I need to go up in oxidation state, so throw in sulfate, because ites go to 8s in this process. And 4 times -2 is -8, but reserve 2 of them for the overall charge, so that's a +6. So I have my oxidation and I have my reduction. All right, so I'm going to get rid of these little charges so I don't confuse them when I look at them again with the overall ion charge at the end of the process. So I'm going to rewrite that as -2 and rewrite that as -2. And my S disappeared, but it will come back and it'll look ugly in a minute. Alright, so what's the story here? Can I do this by inspection? No, this is too hairy, woolly, obnoxious for me to do by inspection. So I know when I'm beaten, I'm going to do it half reaction, because I'll be just as fast as getting frustrated. So who's being reduced? Cr2O7. 2- charge. What's it being reduced to? Cr3+. I need 7 waters. How come? I had 7 O's on the left. That introduces 14 H pluses. And now what's the total charge on the left? I've got +12. What's the total charge on the right? Well, first of all, I need 2 of those. So that's +6. So I've got +6 versus +12. So what's the story? I need to add 6 electrons. Reduction is gain of electrons, 6 of them. So one more time. +14 -2 is +12. 6 electrons give me a +6 total over here, which matches up with my +6 total on the right, so I'm happy with that. So what's the oxidation half? SO3, sulfite, going to SO4, sulfate. I need another oxygen, so I put a water. That's going to force 2 H pluses over here. Got some cleanup work to do in a minute, don't I? Alright, so what's the story now? I've got 4 O's on the left, 4 O's on the right, 1 S, 1 S, 2 H's, 2 H's. Let's do the total charge. Total charge on the left is 2-. Total charge on the right is 220, so I need 2-, and this is the oxidation electrons are lost. OIL, oxidation is lost, so I'm going to lose 2 electrons. Let's do the charge one more time. 2 minus on the left. These H pluses zero out the 2 minus on the sulfate, so I have 2 minus on the right, so we're good. We're balanced with charge. But we have a little bit of cleanup work to do. Got H pluses on both sides, got waters on both sides. So we will cross that water off, leaving 6. We will cross both of those 2 off, leaving 12. Now, what else do we need to do? Oh, you know what? I screwed that up. I have an undo button. Do you have an undo button? Oops, that was a redo button. Undo, undo. I hit it a few times, huh? I did not balance my electrons first. That was a doofus move. One more. Okay, so let's balance the electrons first, which is easy. I need 3, because that's got to go to 6. So everything's got to be multiplied by 3. So I need 3, and that's going to go to 6. Got ahead of myself. Now I can deal with the H pluses and the waters. So 3 waters versus 7 waters. Lose all of those. This reduces to 4. 6 H pluses versus 14. Lose all 6. This goes down to 8. The whole point of this was to cross those off. So now clean up. Cr2O72 minus plus 3SO32 minus plus 8H plus yields 2Cr3 plus 3SO42 minus plus 4H2Os. Total charge over here. 8 pluses minus 6. 3 times minus 2 is a minus 6. It leaves me 2 pluses. So I got 0 on this side. And 2 times plus 3 is plus 6. 3 times minus 2 is minus 6. I got a 0 on this side because the water's 0. So check. We're balanced. Like I said, question 4 in the present day, when we have to balance these equations, may throw one at you where you're going to have to do the half reactions. So practicing is only going to make you faster. Practicing is also good for the multiple choice because you're going to have to do 1 or 2 of those in the multiple choice. So this, however, is hairy, and it's most likely not going to be on question 4, but it doesn't mean that you don't need to know how to do it. Because you're going to go to college. You wouldn't be in this course if you weren't thinking about it. I was the first person in my family to go to college, first person to graduate on time, with time being 5 years, not 4. The other people went to college after me, like my father. He's got 2 degrees now. He didn't as a young man. He went into the military. All right, so let's look at this one. Solutions of potassium iodide, potassium iodate, and dilute sulfuric acid are mixed. Ooh, very interesting. So what do we have going on? Well, we got the sulfuric acid, so we know we have H plus going to H2O. What we don't know is this sulfuric part, the SO4 part, going to participate in this? And the answer to that is, I don't think so, because potassium and potassium aren't going to do anything. So those are spectators. So I have I minus and I have IO3 minus, iodate, like chlorate, only sub the I for the Cl. And so the dilute sulfuric acid is there just to acidify the mix. So this could have very easily said acidified solutions of da-da-da are mixed. So what I have going on here is iodine with a -1 oxidation state, iodide, I should say, with a -1 oxidation state. And the I in iodate is 3 times -2 would be a -6, but to get a total of -1, this has got to be a +5. So I have this one puppy, iodide with I -1, and the +5 oxidation state on the I in iodate, both converging, one oxidized, one reduced. This is a malproportionation reaction. And I told you the halogens are the usual suspects for such things. So what do I write? Let's go with I minus, and let's go with iodate, plus that H plus, and I'm going to scoot the H plus over because I'm going to have to probably put a coefficient in front of it before it's all said and done. And I'm going to make water, and I'm going to make I2. What you have to decide now is, are you going to try to do this by inspection, or are you going to do this by half reactions? And I'm going to go with half reactions because I got a I -1 and a +5. It's a big swing, and these are going to get a little trickier. So let's do it. One of them is easy, one of them is difficult. What's easy? I minus going to I2. That's easy. I minus, going to a higher oxidation state of 0. So I would need 2 of these, and more room. I would need 2 of those, and what else? I need 2 electrons as oxidation. Oxidation is loss, so 2 electrons have to come off over here, so I'm minus 2 on both sides. That was the easy part. So now let's deal with IO3 minus going to I2. It's going to get interesting. Both things are converging on I2. It's, again, called a MAL, M-A-L, proportionation reaction. No one's probably going to ask you that, but I just feel obligated to educate you. All right, so I've got 3 O's. Well, first of all, I need 2 of these. Now I have 6 O's on the left, so I need 6 waters. Doesn't that force 12 H pluses? And I got to add some electrons because reduction is gain. How many? Well, not too bad. I got 0 on the right for a total charge. I have plus 12 and lose 2 of those, so isn't that 10? Plus 10 electrons. So everything here needs to be multiplied through by 5 so that I can have 10 electrons here. Whole point of that is to do that. I have no waters or H pluses to clean up, so I get 2 IO3. What happened? Oh, 5 times 2 is 10. Maybe something wasn't right there, right? 5? 5, 5, 5. I didn't multiply properly. So I have 10 I minuses. 10 I minus plus 2 IO3 minus plus 12 H plus. So I write 11. 12 H plus yields I2 plus 5 more I2, which you know I'm going to combine to 6 here in just a second, right? Plus 6 H2O. So let's clean this up. This is going to be 6 I2. 10 to 12, 6, 6, crap. 5 I minus plus IO3 minus plus 6 H plus, you've caught on now what I'm doing, right? Plus 3 I2, had to get a prime number in there somehow, got the 5 in the beginning so that works, and 3 H2O. Total charge on the right is 0, I better get a total charge on the left of 0. I see 5 minus 1s plus another minus 1 is minus 6 and 6 H pluses, so we are good. 0 on both sides. So check. There's my answer. Now, had you left it doubled, it's still balanced. So you would have gotten that point in today's market, the way we grade it now. You'd have been okay. But I just needed you to... But if you're in the middle of a free response in electrochem and you're about to do stoichiometry with this reaction, that could lead to trouble. You always want to glance. Be on the lookout for evilness such as, oh crap, all even numbers. I got to cut this puppy in half. All right, let's look at the next one. Oh, he's blue. A solution of tin 2 sulfate is added to a solution of iron 3 sulfate. I'm going to get this ugliness out of your way so you can focus better. So, or maybe it's me, maybe I can focus better. The sulfate's on both sides, that's a spectator. So this is an easy one. This is one metal of one kind and another metal of another kind. I call these the easy greasy ones. Metal plus metal and halogen plus halogen. Easy greasy ones. Somebody's going to oxidize somebody, somebody's going to reduce somebody. So you have to think about what you know about tin. Can tin be oxidized? Can it be reduced? Is what you ask yourself. Can it be oxidized? Yes. It can be tin 4. So tin 4 is possible, and that would be an oxidation. Can it be reduced? Yes. All metal ions can be reduced to the metal, so there you go. So it can be reduced. This one can go either way. Then what about this one? Iron 3. Well, iron 3 is the highest oxidation state of iron, so you have no choice but to be reduced. You've got 2 choices what you reduce to. So you can go to iron 2 plus or iron 0, but either way, you're only reduced. So this is going to be one of my players because all iron can do is be reduced. So SN2 plus Fe3 plus yields you got to decide what you're going to do. 4 plus here is no decision, but the Fe3 plus, what are you going to do? Are you going to go all the way down to the metal, or are you going to go to 2 plus? I'll show it to you both ways, because this is easy. It won't take long. Let's put that plus a little closer to the 2, so it doesn't be confused with that plus. So what's the story on the top one? I've got plus 5 versus plus 6. What to do? Well, we could try a 2-3 trick and see what happens, but let's just dive in and go kind of simple. If I double this, I'm going to have to double this. So let's see what that does. Now I have 3 plus, so that's 6 plus 2 is 8, and I have plus 4, and then 2 plus 2 makes 8. So we got there. But it's just trial and error at this point. So 8 plus on each side, that one's balanced. What about the bottom one? On the bottom one, not so lucky, huh? This one's more difficult. So let's try doubling the iron again, see what happens. Just dive in and do something. So I've got plus 6 and 2 more is plus 8, and I've got plus 8 on the other side. Did that do it? Oh, I wrote this wrong. That's supposed to be 0. I was going to say that was too easy. Okay, so try again. I've got plus 6 plus 8 plus 4. If I did, let's go plus 12 on both sides. If I did this, if I went 3 of these, I'll do it in red. 3 of these and 3 of these. Okay, so I've got plus 6 and plus 6 is plus 12. I'm trying to get a 4-3 thing going on over here. 3 times 4 is 12. Yay! Alright, managed. Okay, so clearly the top one was easier, but you have 2 choices. Like I said earlier in this recording, there are more possible correct answers to these than what you're seeing me do. I'm just doing the ones that are most likely and most expected. That doesn't mean that you can't come up with something by design, or let's admit by accident, that is correct. Alright, let's go to metallic copper. Metallic copper, that's going to be fairly straightforward, is heated with concentrated sulfuric acid. So I'm going to need H plus and SO4 minus, and when it's concentrated sulfuric acid, we make SO2. We know we're going to make some water. And we know we're going to take that copper. Again, you have to decide. You're going to get a plus 1 or plus 2. Plus 2 is the more common oxidation state, so I'm going there. It would be blue in solution. Alright, so can we inspect this one? Can I be so lucky? Let's deal with those O's first and see what works out here. You know what? Actually, I think I'm going to go ahead and just do the half reactions. I think I'll waste time. So you gotta know when to fish or cut bait. I'm gonna cut bait and go to the half reactions, because one of them is super easy anyway. The oxidation one, right? Cu0, Cu2 plus 2 electrons. To get 0 on both sides, oxidation is lost, lose 2 electrons. So that leaves me with the sulfate going to SO2. So I would need 2 waters to get 4 O's on both sides. That just gave me 4 H pluses. The right side is completely neutral, so I need 4 electrons. So that means double everything on the bottom, add, and I'm done. See, sometimes it is faster. 4, 2, 2, add, cross, cross, nothing else to clean up. SO4 minus plus 2 Cu, you do not have to put the 0, I just like to, plus 4 H pluses yields 2 Cu2 pluses plus SO2 plus 2 H2O. Total charge on the left, a minus 2 and a plus, and 4 pluses is a plus 2, plus 4, oh crap, what happened? Oh, why do I have a 2? Ah, I can do that and it stays balanced. And now I'm balanced by charge. Well, that was a sneaky little thing. Okay, let's try that again. 2 minus and 4 H pluses gives me a plus 2 on this side. I did have plus 4 over here, and that was troublesome. because that wasn't letting my charge balance, but everything else was balanced. So you know what? I can get rid of those 2's on each side, and that gives me +2 total over here, and I am balanced. It was a legal maneuver. Even though it felt sneaky, it was legal. Alright, moving on. I'm going to try to get through 10 or 12 of these before I quit and move on to a different recording. So, manganese 4 oxide. So they're telling me that this is Mn plus 4O2. Okay, MnO2, manganese 4 oxide, that's right, is added to warm concentrated hydrobromic acid. So there's a halogen, so we're going to get the bromide go to the bromine, and then the MnO2 is one of those things that you had to give up and memorize. MnO2 goes to Mn2+. So I'm not making this stuff up. Alright, so let's see what we get. MnO2 plus H plus Br minus, strong acid dissociates, Mn2 plus Br2, so I would need 2 of those, plus H2O, because I have H plus, I'm always going to have H2O, and I would need, what, to get this to work? Alright, I've got O2 on this side, so I need 2 of these, so that forces a 4 here. I already have a 2 there. What's the total charge on the left? +2. What's the total charge on the right? +2. That one was I could do by inspection. That was worth trying. Alright, so that one was fairly straightforward. Let's see what we have going on in the next one. Now, this one is one that would easily show up now, because that was not so painful. This next one, also pretty good, I think. Chlorine gas, that's Cl2, is bubbled into cold dilute sodium hydroxide. Is sodium going to participate in this? No, because the worst that's going to happen is make sodium chloride, so that's a spectator. So OH minus. So Cl2 plus OH minus is going to yield water. Just like when we add H plus on one side in a redox and have water, if we have OH minus on one side, we're going to have water on the opposite as well. Now, chlorine in basic solutions. That was one of those things that you have to know. I know this can make you dizzy. What's the story? In basic solutions, free halogens go to the hypohalite ion, hypochlorite. Hypochlorite, ClO minus. Now, that got me from 0 to an oxidation state on the chlorine of, what would that be? +1. So that's my oxidation, but what's my reduction? Well, just make Cl minus. When you make Cl minus, now you have a reduction. So here I have one species being both oxidized and reduced. That's a dis, not a mal, but a dis proportionation reaction. Okay, so what's the scoop? I've got 2 chlorines on both sides. That's cool. I have 1 O on the left, 2 O's on the right. Need a 2 there. 2 H's, 2 H's. Total charge, -2 on the left. Total charge, -2 on the right. Another one I could do by inspection. Yay, that's an easy one. Yay, that's an easy one. These are candidates for things that you might see currently. All right, I'm going to try to get through 12 because I have 48 of these, so if I did 12 per recording, that's probably a good plan. All right. Solid iron 3 oxide. So I have no choice than to write Fe2O3 solid. So let's do it. Fe2O3 solid is heated in excess carbon monoxide. So we're not a complete combustion here. What are we going to do? Well, I'm going to go all the way to the metal. See how that works for me. And then here's a +2 on the carbon. If I go to carbon dioxide, because I got my reduction, right? I've got iron 3, Fe3+, going to FeO, and not O as in oxide, 0 as in oxidation state, the metal, solid. And then I need something to be reduced, oxidized. Which way did I just go? I just did the reduction. I need the oxidation. So C can go up from +2 to +4, because it's plus 4 in carbon dioxide. So that works. Can I do this by inspection? I don't think so. I have to make a decision, so don't waste a lot of time making the decision. Just do it. You may find that you just want to always do this. Maybe easier on you. Fe2O3 is going to go to at least 2 of these. And then what? I need 3 waters. So I need 6 H pluses. Do I need anything else? Yes, total charge. 6 plus on the left, 0 on the right. Ooh, easy enough. 6 electrons. All right, how about the oxidation? CO goes to CO2. So I need a water over here. So I need 2 H pluses over here. Got it, got it, got it, got it. And I need 2 electrons and 0 on both sides. Yippee skippy. Okay, so triple everything here so that I can get 6 electrons. So that I can cross them off. Alright, I got 6 H pluses on both sides. How convenient. I've got 3 waters on both sides. Doubly convenient. So I may have been able to do that by inspection. Fe2O3 plus 3CO yields 2 Fe plus 3CO2. Did I leave anything out? Nope, nope. Total charge on the left. 0. Total charge on the right. 0. 3 Cs, 3 Cs. 6 Os, 6 Os. 2 Fe's, 2 Fe's. I'm happy with that. So that one was not terribly painful. Alright, let's finish this set off. Hydrogen peroxide solution is added to acidified, there's our good buddy H plus to make water, potassium iodide solution. So we're going to cross that out because that's a spectator. I feel a sneeze coming on, I'm warning you. Hydrogen peroxide solution, H2O2, is going to make oxygen and water. Well, it's going to make water. So let's go to water. And then what else is going to take place? My I minus is going to go to I2 because that's going to be an oxidation, right, from a -1 oxidation state up to 0, whereas the peroxide has that peroxide ion, O2 minus 2, that's going to go to the normal oxygen of the water. And what else do I need? Oh, it said acidified. Plus H plus, and I already had my water there, so that's just all well, fine and dandy. Alright, so let's see what's going on. First we need to do that, so we've got to balance that. Alright, so I've got a bunch of H's to play with here. So if I need 2 O's, so I'm going to force a double there. And if I put a 2 there, I get 4 H's on each side, so that worked out nicely. And the total charge on the right is 0, and the total charge on the left is also now 0. So that one was actually easy. Yay, an easy one. Alright, that's going to finish off this set of the first Dirty Dozen. We're going to move into the next Dirty Dozen, and then there will be 2 more dozens after that. Again, I don't think you need to listen to each and every one. I think you could pick and choose, but if you did poorly on this set, then it is definitely worth your time to spend some time listening to the next set. There'll be same song, second verse, before the third verse, and the fourth verse come around. So I hope you have a great rest of your day. Until next time, this is Renee McCormick, signing off.